Let's take a look at how to implement some of the basic functional blocks we have covered in this lecture. First of all, we have value fixing. To show you how to do value fixing, let's first get a binary probe as our target. Let's say this is the wire upon which we want to fix a constant value of 0 or 1. In fact, let's copy this and do 0 here and then 1 for this wire. To provide a constant positive value, what we can do is we can search for a 5-volt power source like this. We place it here and connect. Check the connection, which is indeed connected, and you can see the value fixing has been performed correctly. And further down, if you want to pass it to subsequent gates, such as an OR gate, you can easily do so by performing this kind of connection. It will always remain a positive value because this is a constant. On the bottom side, if we want to fix a zero value onto this wire, we will need to get a digital ground. You drag out a digital ground and then perform the connection. You check that it's indeed connected, and as you can see, this wire now carries a negative value. This is called value fixing. Once you know how to do value fixing, let's do transferring. Transferring is very simple. Let's assume that you have some sort of existing values. Let's get ourselves a binary switch. And let's assume that this binary switch contains value for variable A. If you want to transfer this value onto a different wire, let's say this wire is carrying the value of variable B. You just connect them. In this case, you might get a naming conflict that just shows A over here. Yeah. From one wire or one source to a target. This is called transferring, which I'm pretty sure you have already done in the past. We're just giving it a new name. The next step is to do transferring. Let me first of all copy the input switch over here. This is inverting. Inverting can be simply done by using a NOT gate. You place the NOT gate over here. Assuming this is your target, you connect the wires. And this is all there is for inverting. To use the multi-bit functions, or to be more specific, to use the vector denotation, we're going to need something called the buses. You probably have already seen tutorials to do buses in a previous lecture. What we can do over here is we can go to schematics, new breakout, and over here we'll first need to define the symbol. Let's say we're going to call this bus D, and then we're going to need to provide a list of pins, let's say from 0 all the way to 3. Pin spacing was also discussed in the previous lecture, so let's click OK, and this will create for us a nice breakout for buses. For this example, I'm going to use my trusty hexadecimal keyboard to provide input. Let's say we want 4 bits of value, 4 bits of binary value, to be transferred on a single wire instead of 4 separate wires through a long distance. And on the receiving end, let's pretend that we need a hexadecimal display. Again, it is very important when you're using the hexadecimal display and the keyboard, you need to make sure the most significant digit is on top, over here. The most significant digit on a hexadecimal keyboard is on the same row as 0, 1, 2, 3. This is the least significant digit, C, D, E, F over here. For a hexadecimal display, the least significant digit is noted by the solid black dot over here. You will also need to do another breakout on the output side. Let's copy this one over here, paste it, and then flip it horizontally, so it is perfectly aligned with our display. Connect the wires, and then, oops, seems that we have a small mistake over here. One of the wires were accidentally connected. We need to disconnect it. We can use the zap tool in the toolbar to remove this connection, and then re-establish connection over here. Check that everything is indeed connected correctly. I can see this one is not connected, so we need to, let's remove this and reconnect. Again, if something is not working, always check for your connections. You can check the connection by highlighting individual wires like this until you find the breaking one. As you can see, in this case, we can transfer 4 bits of information through a long distance through a single wire instead of 4 separate wires. We can even expand this. Let's say if you want to transfer an 8-bit number through a long distance, you can of course create a new breakout, D0 all the way to 7. This is 8 pins. Connect, and then we can very easily transfer 8 bits of signals through a long distance. Input 5F, output 5F on the other end. And finally, we can try to implement for us an enabler. The primary idea about the enabler is that you would have your standard value to be transferred. Let's say this is value X, which contains the value to be transferred to a different source. Let's get the source over here. With ordinary value transferring, you will simply connect these 2 wires, and then the value of X will be transferred to the target side. With enablers, you would instead create a separate input and name this as EN. And then you insert the enabler between them, usually using an AND gate. So now what happens over here, if EN is 0, then no matter what you do with the value of X, your output will always be 0. The value does not get transferred. If you flip the EN signal to 1, then your target output side value will equal to X. Right now X is 0. Let's flip it to 1. The output is 1 as well. This can be easily proven by using the binary identity. So there you have it. The 5 very basic functions. Value fixing, providing a constant of 1 or 0 to a wire. Value transferring, basically just connecting up 2 wires. Inverting the value, using buses to carry multiple bits across a long distance. And then finally, implementation for an enabler.